Section 4.6 is going to focus on some specific triangles. We've talked about an isosceles triangle, what an equilateral and right triangles are each, but we're just going to go a little bit more in detail. We actually going to spend 2 days on this section. The focus today is going to be on isosceles and equilateral, and then we'll spend some time on right triangles tomorrow. Okay?
Sounds great.
All right, so isosceles triangle. We already know by definition isosceles triangle has at least 2 congruent sides. So I drew one in here for you. What we need to elaborate on are some of the pieces of an isosceles triangle. First of all, base angles. All right, now notice it's plural, so that means...
So there's probably more than one of them.
More than one. And these are 2 angles that are adjacent to the base. Okay, so before we can actually label what that is in this picture, going back to when we very first day of this chapter, we talked about an isosceles triangle, had at least 2 congruent sides. Now, what do we call those 2 congruent sides?
We called those the legs.
So this is a leg, and this is a leg.
And the base was the side that was not a leg.
Yeah, so in other words, the non-congruent side.
Exactly.
Okay, so if base angles, notice the name goes along with this idea of a base, are 2 angles that are adjacent to the base.
Okay,
so kind of
and
next
adjacent,
to that.
kind of connected to that. So I would say angle J and angle P would be considered my base angles. They're the angles along that base.
So angle J and angle P are your base angle. So these 2 right here, this one and this one, these are your base angles. So there's one and there's one right there. All right, now the other type of angle that we're going to talk about is a vertex angle. And a vertex angle is just the angle opposite the base.
Okay, so it's the one that's connecting the 2 legs together. So angle K would be my vertex angle.
Yeah, and notice it's across from the base in a sense.
Yep.
And I like how Ms. Hograby said it. She said it connects the 2 legs. So notice it's the one that is created by the 2 legs. All right, now the reason why you need to know this vocabulary, what base angles are, vertex angles are, is there's an actual theorem that involves base angles.
Imagine that, another theorem.
Oh my gosh, holy moly, would have never guessed. Now, this is something that some of you kind of had a hunch about a little while ago, right? In a isosceles triangle, we already know we have at least 2 congruent legs, 2 congruent sides.
Right.
Isosceles triangle also has some congruent angles.
Oh, okay.
Okay. So let's take a look at this theorem, and maybe some of you are already thinking it.
And this is the base angles theorem. And we're going to use the acronym BAT, or BAT for short. And this base angle theorem says that if 2 sides of a triangle are marked congruent, so in this little picture I've got, if these 2 sides are marked congruent, then the angles that are opposite those sides. So we know 2 sides of the triangle are congruent. Now we're saying the angles opposite those sides are also congruent. So if this obviously is an isosceles triangle, these are the 2 legs, those base angles are going to be congruent as well. Okay. So given this picture that I have of triangle ABD, and we know that side BD and AD are congruent, what else do we know?
Okay, so if BD is congruent to segment AD, then I know the angles opposite those sides are going to be congruent. So angle B and angle A are going to be congruent.
Yes. And you know that we in proof, or especially when we're talking about proving triangles or even using that CP/CTC after we've got triangles congruent to proving other parts congruent, we like to be able to have some congruent statements. Mm-hmm. So the nice thing about this is it gives us more pieces that we can talk about that are also congruent.
So this does not prove triangles are congruent, right?
Correct. It only proves other parts are congruent.
So this
it proves the angles are congruent.
This is proving angles are congruent. And it doesn't, notice it's only involving 1 triangle. So you don't have to be talking about 2 triangles here. And it's actually only involved in a triangle. So essentially, if you have an isosceles triangle, right, then its base angles are congruent. That's really what it's saying.
Right.
Okay. Now, what if I gave you a triangle with 2 congruent angles? What's your guess?
Well, then the sides should also, those opposite sides, those legs should be congruent as well, right?
Which basically, if you're already thinking it, you're basically flip-flopping this. You're starting here and you're ending here. What do we call
Oh,
that?
that's a converse.
You got it. Okay, so this is the base angle theorem converse, or BAT, or BAT converse. And notice it says if two angles in a triangle, so you're talking about in one triangle, are congruent, then the sides that are opposite those angles are congruent. So this time I'm giving you a pair of congruent angles, and then I can say those sides across from them are congruent as well. Okay. So in this picture, angle K and angle H are congruent. Then
we know that GH, that side, is congruent to GK.
So again, the ones that are opposite. So this side is congruent to that side. And this is because of the base angle theorem converse. Be careful with converse versus the original.
Yeah, and one thing that I always stress to my kids, the base angle theorem is proving angles congruent. Mm-hmm. So the base angle theorem converse is what, when we already know the angles are congruent, we're
kind of going the backwards of that.
Yeah, so, but base angle theorem proves angles congruent, so keep that in mind, guys.
Okay, now, what if you have all three sides are congruent? Okay, so let's think about this. I already know two. If I know two sides are congruent,
that's what I was thinking.
Yeah, like we know if in an isosceles triangle at least two congruent sides. So here's at least two. If I take away that one, just to kind of talk about it. So if I know that these two sides here are congruent, then what are you gonna know?
I know that those base angles are congruent. So angle A is congruent to angle.
So what if I know, let's say I'm talking about these two sides are congruent.
Okay, then I would know that angle B was congruent to angle C.
And I already know C has one tick mark, B has one tick mark now. And if you look at it and just put it back to how it was, then what did we basically prove?
That if it's equilateral, it's equiangular.
Exactly.
We're using some vocabulary.
Yeah, if all three sides are congruent in a triangle, all three angles are congruent. And this is actually another hunch that some of you had a while ago. So this is the notice what it is.
It's a corollary to the base angle theorem. And we've talked about these corollaries before. They're just kind of more specific cases of the theorem. Getting, with a more specific figure or doing a little bit more with it. The corollary to the base angle theorem says if a triangle is equilateral, meaning all the sides are marked congruent, then it's also equiangular, knowing that all those angles are going to be marked congruent as well.
And hopefully that's logical. And if, some students will ask me, what do I use to write this? I would just call this BAT corollary.
Yeah.
Yeah. You don't have to say corollary to base angle theorem. So BAT corollary.
Just don't say BAT converse, because
we got to
make sure we know that's different. And you won't see this a ton because it's a very specific.
Yeah. Corollaries, remember, are very specific. Remember, corollaries come from a theorem. So this one's coming from the base angle theorem, and it's very specific. So there is the converse of the BAT corollary, and it's just flip-flop what we did. If you know it's equiangular, so all the angles are congruent, then, of course, it's equilateral, which means all the sides are congruent. So going back to very first section, when we classified triangles, now we know this. If we know stuff about the sides, then we can say stuff about the angles, which is kind of nice. Mm-hmm. All right? So just kind of keep that in mind. What if none of the sides were congruent? I know this doesn't have to do with this one, but what if none of the sides were congruent?
Well, I'm guessing when the sides are congruent, the angles are congruent. So I'm guessing if the sides aren't congruent, the opposite angles aren't congruent either.
Exactly. So that relationship happens.
Kind of sounds a little inverse-like to me.
Mm-hmm. You're exactly right. Okay, so here's an example that just before we get to some more proofs as well as that, we've seen something like this. If you know you're given a picture like this and they ask you, is it possible to prove the triangles are congruent? If so, give the congruent statement and postulate the theorem. We've done this a lot. So looking at that picture,
okay,
what is it that you're noticing?
Well, my gut has been telling me that, we've cut two triangles because we've been talking about two triangles so much this chapter.
Yeah.
That's something that I see right away.
And in between those two sides,
I've got a reflexive side, so I know
could
that's
go ahead
congruent.
and say that. Okay.
And they don't really give me anything else here. But I'm guessing that this is going to apply to something that we've talked about today.
Probably good guess.
So, but neither one of those are isosceles triangles by themselves.
No, you're right. We don't really know if segment EA is congruent to ET and EM. But I want you to kind of look at the bigger picture.
Okay.
What do you think? What are you looking at now?
Now I see that it's one big isosceles triangle if I look at it this way. Because I saw that I have two congruent sides.
So these two segments are congruent in one bigger triangle. And if you have two sides in a triangle that are congruent, that means
their base angles are congruent.
So which ones are going to be the angles that are going to be congruent?
Angle T is congruent to angle N.
And that's because of...
Let's see, I proved angles congruent, so the base angle theorem.
Good. All right, so if you look at that,
okay,
this is kind of what's happening here.
All right, let me see. I've got two sides. I've got three pieces. That should be enough. Are they in the right order, though? Because I'm seeing...
Here are the two triangles we're looking at.
Ooh, this looks like that's going to spell a bad word.
Let's see. Is the angle included?
It's not included in an angle side. Does not sound like something that we want to use in class.
This is how gravy. Let's be G-rated.
Okay, so I'm going to say that it's not possible.
It isn't possible. Now, we did come up with three congruent pieces, but that side-side angle relationship is not a theorem. It's not going to work. It's just not possible. All right, and there's not enough information to prove these angles are congruent. We really can't prove these angles are congruent. We don't know anything about these sides. Okay, so first and foremost, I see there's actually three triangles in this picture.
There are.
The kind of like the last one where we were kind of doing it, there's three different triangles. They're not asking anything about proving congruent triangles, so I don't really know if that's anything to do with it. I do see that's asking for X and Y. So I notice X is an angle in one of the smaller of the two triangles, or three triangles. Y is an angle actually in one of the smaller triangles, but also the bigger one.
Okay.
But kind of looking at the two smaller, both of those triangles have a pair of congruent sides, which kind of goes along with this isosceles triangle idea that we've been talking about. So that's probably where I'm going to lean forward to first.
I think that sounds great.
And I'm going to start with the triangle that has the angle 50 labeled because that actually might help us. Okay. So I know that in that triangle with the 50, that 50 represents the vertex angle.
Nice vocabulary.
And the fact that these two sides are congruent, that means the base angles, the other two angles, are going to be congruent to each other. So that angle that's not labeled is going to be the same as X as the other one. Those are going to be the same value.
Sure.
So two ways I think about this. I know that now I have three angles labeled, and in our triangle, all three angles add up to 180. So I can say X plus 50 is equal to 180. That would work, right?
Right. That's using that triangle sum theorem.
Okay. Now, another way, and I think this is a way I see a lot of students doing in the past, is if you know the vertex angle of an isosceles triangle, if I just take 180 minus that, so my 180 minus 50, sorry, that's 130. Now, is 130 going to be that one X? No, that's the sum of those two X's. And since those values are exactly the same, I can just cut that in half. And that's going to get you 65. So that's what X equals, which means both of those base angles are 65. So if they ever ask you to find the base angles of an isosceles triangle, given the vertex, you can.
Right. And we could have even said that the two X's together equal 130.
Yes.
You would have gotten to this if you'd have combined like terms and solved up here. Same thing here, just, X is 65.
Okay, so I'm halfway there. I need to find Y. Okay, so I'm looking at the triangle, the smaller triangle, since it's another isosceles triangle, but I can't really do exactly what I did there yet because I don't have that vertex angle.
Right.
But,
in fact, there's no angles marked in there.
Yeah, okay. But I see that value that's labeled X right next to it that actually forms a linear pair with the vertex angle. So I can use linear pair postulate and find that vertex angle, take 180 minus 65, and that's going to get you the 115.
So this angle is 115.
Okay, so now I can kind of do what I did on the last one. I know the vertex angle, and to find the base angles of that, which are technically both Y, I could take 180 minus 115, and that gets you 65.
And that right there should be the sum of both of these, right?
Uh-huh. And then I just cut that in half. And that's going to be what y is, which is 32.5. Now, I don't know if any of you were hearing this, but I felt like I repeated myself a couple times. Like, I felt like, okay, well, I did 180 minus 65 to get the 115. And then I did 180 minus 115, and I went back to 65. So another way to think about this, which is not always so obvious, is that 65, that x, is actually an exterior angle to that other triangle. And we learned earlier in this chapter that exterior angles measures are made from the two non-adjacent angles sum. So that 65 is actually equal to 2y. And then you can just cut it in half. There's where you're getting the 32.5.
Right. And if you remember that exterior angle theorem, which hopefully you do because I can tell you that might be a good test question later.
Yeah, for sure.
But that if you see that is an exterior angle, that can give you kind of a shortcut, really, on this one. Awesome.
All right, so another one, finding value of x and y. Notice again, the last one, I first was thinking congruent, maybe doing with congruent triangles, but it didn't. So not everything in this chapter is involving congruent triangles. It's maybe talking about something about the triangles. So right away, you look at the two triangles that are in this picture. Do we know if they're congruent?
I kind of doubt they are.
Yeah.
Because one's got 2 tick marks on its 2 sides, 2 legs. The other one's only got 1 tick mark on its 2 legs. But I can tell they're both isosceles.
Good.
Which that kind of seems to be the key this section so far, too.
So the isosceles, and this is more specific when you see 2 congruent sides in it. Okay, this isn't always going to be the case, but when you see that, think about what we know about isosceles triangle. All right, so let's start there. What do you know about isosceles triangles?
I know that their base angles are congruent.
Okay, so
I know that, like, for example, the 7y minus 3 is congruent to the 3y plus 13.
Yeah, because if these legs here are congruent, those two angles that are across from are congruent. So if those angles are congruent, I can
make an equation.
Yeah.
Because I know that 7y minus 3 should equal our 3y plus 13.
So we go ahead and solve. So I get 4y is equal to, what, 16? So y equals 4.
Right.
So we found that value. We're halfway there.
Okay. Then I could find out what the angle measure is.
Okay. Now, before you do that, I mean, can we do what we did, like, down here? Aren't these going to be congruent?
They are, but I don't have anything else on the other side to really talk about.
Can I just say it's 2x plus 3?
Oh, we could say it's 2x plus 3.
Yeah.
Sure.
But
that's not helping me solve for x.
Yeah, because I said it equal. 2x plus 3 equals
Yeah, that'd be an
2x plus
identity equation.
Yeah,
because you're saying
that's
something
not going to
equals
really
itself.
help us any. Okay.
Right, okay.
So I'm just kind of thinking about what you were doing and maybe going off of that, but that doesn't really help us. So
No, but I do see, looking at this picture, I see some vertical angles that are congruent. And I see that if those vertical angles, and I know that the base angles of the other triangle are congruent to each other, but can I almost use the idea of like a third angle theorem idea here or something to say that if I know that it's not really the third angle theorem, but I've got altogether they're 180 degrees. So if I take 180 and subtract the vertical angle top part of that, you know, the one that's the vertex angle of the top triangle, what I'm left with should be the same thing as if I took 180 minus the vertex angle of the bottom triangle and divided that by 2.
Okay, let's go through what you're thinking, how we're gonna do this.
Okay, let's go ahead.
You got some ideas.
I've got some thoughts going.
You got some thoughts, and I think you're on the right track.
Okay, well, let's talk for a minute about, we know what those angles are now of the top triangle. Because we know that the top triangle, we have the 3 times y plus 13. Well, 3 times 4 would give me a 12.
So you're basically substituting.
I'm just substituting them in.
And why not? I mean, if
we
you
know what those
already
angle
know what
measures
it is, put that in. So you get 25 degrees for this angle right here.
Exactly.
Which means this should also be
25, which
25.
if I check that, 7 times 4 is 28 minus 3 is 25.
So it works out. Okay.
Now so now I'm thinking that third angle that I've got there, the vertex angle. If I did that 180 minus really the 50 that I've already accounted for,
Okay.
that's going to give me 130 degrees.
Let me write that down. So she got the 50 from the 225s.
Right.
And so that's this vertical angle right here, right?
Right.
Which means that's this.
That's also 130.
Okay.
And if I know that those two angles are going to be congruent because of the base angle theorem, I know that they're each going to be 25.
You're exactly right. So this is kind of what Ms. Hokgravy was saying this earlier. And I think just kind of seeing a visual of this is good. She's basically saying that these base angles and this one kind of on the bottom of the bottom of the two triangles, these base angles are going to be the same as the base angles up top because of the fact that their vertical angles are exactly the same. Okay? Now, that doesn't prove these triangles are congruent by all means. It just proves that we have some congruent angles in the mix.
Yeah.
Now, if you don't see that, you could still find the value of x without finding these angles down here or down here. Okay? But knowing that these are 25, how do you find x?
That 2x plus 3 equals 25.
So when you do that, you get 2x is equal to 22, so x equals 11. Now, again, what I was saying, what you could do is, let's say you don't see that these are going to be 25. Well, you found this vertical angle 130. You know that's going to be 130 as well. So you could do triangle sum theorem, right? So 130 plus 2x plus 3 plus another 2x plus 3 is equal to 180. And guess what?
You'll end up with the same thing.
So there's a variety of ways to approach it. The big key to this problem is starting with the fact that you have isosceles triangles and knowing base angles are congruent. And in this case, the fact that they share the same vertex angle, that's important. Okay.
All right, let's take a look at this stuff in a proof. So first of all, we know in this example that we've got some angles that are congruent. We have angle E is congruent to angle H, and we also have a set of sides. Segment EF is congruent to segment GH. And I'm going to go ahead and mark that in my picture. So we know that angle E, which I know has to be talking about this one, is congruent to angle H. And I know that EF is congruent to GH. Now, let's take a look at where we're going. We're trying to prove that DF, this segment right here, is congruent to DG, this segment right here.
Okay.
Okay.
All right. So I'm looking at that, and I see several triangles in this picture. I see the fact that you're trying to prove DF is congruent to segment DG. I'm noticing those are part of kind of those two outside triangles, DEF and DGH. And I know from yesterday that if I could prove those two triangles are congruent, DF and DG are congruent as well, right?
Correct. That's true.
Okay. And the reason why I'm kind of leaning towards that, because what's the given? The given is telling you stuff about angle DEF or triangle DEF and triangle DHG. So we already have two congruent pieces. If I can come up with a third congruent piece of that, then those two triangles are congruent.
Correct. And notice that she's talking about these triangles right here.
Yeah.
Because they do have an overlapping part, and that's the only overlapping part we need.
Okay.
Right? And they give us a segment of that triangle and an angle within those triangles, too.
Okay. So I obviously won't be able to say anything about DF and DG yet. Okay. But what I am noticing is that angle E and angle H, are congruent. And those are actually part of the bigger triangle.
Yeah, and notice the way that they give it to you. Angle E is congruent to angle H. As soon as I marked that, I immediately thought to myself, oh, that's one big triangle.
It's part of one big triangle. That triangle DEH. And if that's the case, if I know some base angles are congruent, then I know the opposite sides are congruent. So I could say segment DE is congruent to segment DH. Why don't you label it with two tick marks just
Good
to be
call.
on the safe side.
And we know that because of?
Well, I'm proving the segments are congruent, so that means the base angle theorem converse. Now, and that helps me because now I can say those two triangles the smaller triangles are congruent. So I can say triangle DEF is congruent to triangle DHG because of side, angle, side. And once I have congruent triangles, I know their corresponding parts are congruent, which is DF and DG. So those are congruent because of CPCTC. Not very long. I was kind of thinking it was going to take some time, but...
Yeah, it's nice to know more reasons because it really does help us. Now, I'm going to go back for a second because you said this was definitely base angle theorem converse. And you're right, because we know that when we're proving the angles congruent, that's the base angle theorem. But here we already knew the angles were congruent, so we did the converse. We used base angle theorem converse to show that the sides are then congruent. Awesome.
All right. Let's do this one right here. It says if, all right, we got a lot in the given. If E is the midpoint of segment AD and angle A and angle D, if I can write this right, are right angles, and angle 1 is congruent to angle 2. So lots in the given. Let's kind of feed off of what we know.
Okay, so I'm going to just start with my first piece of given.
Okay.
And let's talk about what all these things tell me. So if E is the midpoint of segment AD, then we know that it's dividing a segment into two congruent segments. So I know that AE is congruent to ED, and that would be the definition of a midpoint. So when we see that vocabulary word, we're still defining it. Okay.
Let me label the 1 and 2 are angles.
Yes, since they gave that to us in our given.
All
right. Now they also tell us that angle A and angle D are right angles. So as I'm looking at that, we know all right angles. They're not even telling me it's perpendicular where I have to say that they're right angles. They give it to me that they're right angles.
That's nice.
That is nice. And we know the right angle congruence theorem tells us that means they are congruent. So angle A is congruent to angle D, right angle congruence theorem. Now, I haven't really looked at where we're going yet. I'm just feeding off the given.
Well,
and I do that a lot sometimes because it's helpful.
And I do that too because there's a reason why the given is there. But I like that you stop for a second because you're like, wait, I don't even know what I'm proving.
Right.
So let's stop and look at what we're trying to prove.
We're trying to prove that triangle BEC is isosceles. Oh, okay. Now, isosceles. Well, I'm thinking that's a vocabulary word. Mm-hmm. So I probably want to define it. And I know that to define isosceles, you have at least two congruent sides. Okay, I think I know where I'm going. I want to talk about really BE and EC probably being congruent here.
So if I can prove those two segments are congruent,
then I can say that triangle's isosceles.
Perfect.
Okay, now I feel like I have a plan. And I also can tell that with what I'm given right now, I've got 3 congruent statements. And it's 3 congruent statements. Those 3 parts that are congruent are parts of those 2 smaller triangles on the sides.
Yeah.
And that would be angle, side, angle. I can prove these 2 triangles are congruent just with explaining this given information.
And she's talking about these triangles right here.
Yeah.
These 2 right here. And you're exactly right. We can prove these triangles are congruent. So let's do the triangle statement.
So triangle AEB is congruent to triangle DEC. And that right there is angle, side, angle.
See there, angle, side, angle. Good.
All right. Now, okay, I see it. Because now I want to be able to say that those sides are congruent, which I can because of CPCTC. That does follow that congruent statement a lot, doesn't it, Mrs. Palermo?
It does. It happens almost every single time.
So we're going to say segment BE is congruent to segment EC, and that reason is CPCTC. Those corresponding parts of congruent triangles are congruent. And because I know that those are congruent, this is an isosceles triangle.
And I like that when you were kind of thinking through this, since you knew you were trying to prove isosceles, you're thinking vocab. You're like, what's the definition of isosceles? It says 2 congruent sides at least. So we know now that we've proven the 2 congruent sides are congruent, it's isosceles, which means we can say that because of
the definition of isosceles.
Again, that definition idea there.